Hi friends, welcome to this class. In this class, I am going to discuss about Mitsonubu reaction. So, what is this Mitsonubu reaction? See, consider this is alcohol, R dash, and here OH is above the plane. I want same alcohol but inverted in configuration like this OH. So you will tell SN2 reaction. If you do it, we will get the compound, right? So instead of OH, if I have chlorine, and you will tell add NaOH, it will do SN2 reaction and inversion of configuration, and we get the product, you will tell. But the problem is, see, to undergo SN2 reaction, we know that order should be primary, secondary, tertiary. The primary carbon will go easily SN2 reaction compared to secondary, because the steric hindrance matters, right? So here two R group are very bulky, then this OH minus can't attack because of steric hindrance. It can't undergo SN2 reaction. If it undergoes SN1 reaction, we will get racemic mixture. Along with this, we will get the one more product, that is this thing, R dash above OH. So we will get racemic mixture, R and S, right? Like that racemic mixture we will get. But my condition is, we do a reaction, we should get only this compound, purely this one. So how we will do? So the Mitsonubu scientist, he gave a reagent and he did the reaction. The reagents were, he made use of PPH3, right? PPH3 and DEAD, dead, he used. What is this dead? I will give you the structure. So this is N double bond N and COOET, and here also COOET. Valence of nitrogen is 3 and it is satisfied, right? So it is diethyl azido dicarboxylate. So it is diethyl azido dicarboxylate, one and one more. So it is what? Diethyl azido dicarboxylate. What is this carboxylate? Ester group, you should know, right? So this is the structure of diethyl azido carboxylate, dead, DEAD, right? So what he did, PPH3 he added. So this is PPH3 phosphine, right? So you can see here also one electron withdrawing group, here also one electron withdrawing group. So this makes this nitrogen very electron deficient. So this can easily take this electron density like this, right? And this electron density will be stabilized by the electron withdrawing group by resonance. These things you should know, right? So what it will do? It will N single bond N minus this negative charge is stabilized by COOET, and here also COOET. Only we should use this DEAD, dead only? No, it is not the case. DIAD also we can use. I means isopropyl. Instead of ethyl, we use isopropyl. This is isopropyl, CH3, CH3, and this is linked to oxygen, right? This is linking bond, right? Or we can use any electron withdrawing group attached to this nitrogen. Here any electron withdrawing group we can use, and here we get phosphor bond, PH3, and phosphor gets positive charge. So what he did, he took the reagent. Here I have taken alcohol, right? Oh, in this Mitsonubu we need to take only alcohol in presence of PPH3 and dead, that is PPH3 plus DEAD, dead, first reagent. Second reagent, we add any acid. Why we add acid? That thing we will discuss, right? So when we add PPH3 and dead, we got this reagent. So let me have this, right? So this is the reagent. Second step, we add acid. What kind of acid? Any acid, RCOOH. this negative charge, nitrogen having negative charge, it will take this H plus, right? So it will form N, and here any electron withdrawing group, EW electron withdrawing group, right? And here H is there, and here PH3 plus, and here electron withdrawing group, like that I will write. So here alcohol is there, so what happens, this alcohol group is there, R dash double bond OH, right? So not double bond, above the plane, right? So this lone pair will attack this phosphor. So what happens, we get this structure, NH, here electron withdrawing group, hydrogen, here electron withdrawing group, and here phosphor, PH3, and oxygen which is above the plane, and here 2R group, R dash, right? No problem. Phosphor here positive, as it gives lone pair, oxygen gets positive charge, right? And oxygen neutralize this positive charge by taking the electron density from proton and leaving H plus, and it became neutral again, right? And here H plus is there. So this thing we got. Next, to get the same OH in below the plane, what they did, here acid group is also there, right? Acid has taken H plus, so RCOO minus is there, one region, and again we add, to get this OH minus, the base we add NaOH, right? So OH minus will be there, this OH minus form base NaOH. So what happens, we know that phosphor oxygen bond is very strong, right? So this OH minus will attack this, and this bond will be taken, and this electron density will be again given to nitrogen. Why only nitrogen? Because here electron withdrawing groups are there. These will stabilize the negative charge on nitrogen, electron withdrawing group. So this is more electrophilic. Why it is electrophilic? Because phosphor oxygen bond is stronger, it will take the electron density like this. So what happens, here it will form P double bond O, PH, that is nothing but PPH3. I used to write PPH3, means the structure is PPH, and double bond O, right? And here, as it is SN2 reaction, SN2 means inversion in configuration, right? So we used to get R dash below the plane OH, and here we are left with N, single bond N, here electron withdrawing group hydrogen, and here electron withdrawing group with negative charge. As we have acid, that, and also this NaOH, water will be there, so water will be there, from that it will get proton and it becomes NH, right? Here also electron withdrawing group, here also electron withdrawing group. So we got from this, we got this product. But the problem is, here we have taken OH minus in excess, base is there. If we haven't taken this NaOH, then we won't get this product. The product will be, see here, acid, here the acid will be there like RCOO minus, because the H plus will be taken from this negative charge, right? So this negative charge H will be taken, so we are left with RCOO minus, right? So this RCOO minus will attack this carbon, and same PO bond will be stronger, it will take, and this negative charge, and negative charge gets a proton from water. Same product we will get here, and this also PO, PH3 will get, and instead of getting this product, here this oxygen has attached, so R dash from below the plane only, because it is SN2, O, CO, R. This product we will get, right? So to get this product, we need to add base here, excess of base. If only acid is there, then we will get this product, right? If we have, along with that, in third step, if we add base NaOH, then we will get this product. So this is nothing but Mitsonubu reaction. It is nothing but SN2 reaction in which secondary alcohols are inverted in configuration, and we will get anything in inversion in configuration. Here I have used NaOH, so OH I have get. If I use only acid, I will get this. If I use any other nucleophile, right, any other nucleophile, I will get this product. Below the plane, nucleophile will attack, right? So this is nothing but Mitsonubu reaction. So this reaction is nothing but Mitsonubu, right? The same reaction are carried out by some other scientists, like Appeal reaction is there, and also Stondinger reaction is there. We will discuss about them also little bit. In next video, we will discuss only problems on Mitsonubu reaction. Problem means examples of this Mitsonubu reaction, right? So let us see few examples similar to Mitsonubu reaction. One is Appeal reaction. Appeal reaction. So in Appeal reaction, the substrate they will take this alcohol only. Above the plane OH will be there, below the hydrogen. We won't show that below hydrogen, right? So here in Mitsonubu he used PPH3 in dead, DAD, right? You should remember that. And here he used PPH3 along with that CX4. He made use of this CX4, and it is also pure SN2 reaction, and product will be 100% inversion only. Inverted product only we will get. So how the reaction happens, everything we will discuss. And here X is the halogen is there, right? Because of this OH will be replaced and we get the product like this. Below the plane 100% inversion and we get halogen there, right? So how this reaction occurs? This reaction, see here mechanism. PPH3. PPH3 structure you should know, not that difficult. PH phosphine, pH and pH. This is also phosphine. The whole structure is called phosphine, PPH. This is nothing but phenyl group, right? C6H5. So what it will do, it will have lone pair, and here halogen will be there. X, instead of X you can take it as chlorine or bromine, right? Chlorine or bromine, right? So what it will do, it can't attack like this, because here all 4 chlorine steric influence will be there, SN2 reaction not possible. So what it will do, this lone pair will take this halogen and this negative charge will be on carbon. So what happens, PH3, phosphor get positive charge as it has donated the lone pair, and halogen X. Instead of X, here I have taken chlorine, so let me write chlorine, and here carbon getting negative charge and 3 chlorine will be there, right? So 3 electron withdrawing group which are more electronegative can easily stabilize this negative charge by minus I effect, inductive effect. Minus I effect, those will stabilize this negative charge, right? So no need to worry, it will remain in the solution easily, right? So we got this reagent. So what happens, phosphor getting positive charge and halogen is there. So we have in substrate we have alcohol like this, which is above the plane, OH. So what it will do, it will attack this phosphor, as phosphor oxygen bond is stronger, and this halogen will leave, because oxygen gets positive charge. To neutralize that, the proton, not halogen, proton will leave as H plus. So minus H plus, let me write. So what happens, PH3, here oxygen, and here R, yes, R, and this is above the plane, right? And here chlorine is there. So phosphor valency 5, 3, 4, 5, it's satisfied. But we know that phosphor and this oxygen bond is stronger. So what it will do, it will take this bond, right? So this gains electron deficient, and this chlorine will move with the bond and it attacks. It is like SN2 reaction only. So inversion happens. So what we got, PPH3 double bond O. This is double bond O, and this will, and we get R, and below the plane we get chlorine. See here X. So this is nothing but Appeal reaction. Appeal reaction means alcohol will be there, PPH3 in presence of CX4 we will use. In presence of DAD it will be Mitsonubu reaction. Both are like SN2 reaction, 100% inversion, and the mechanism I have given you, right? Same thing. The phosphor is valence is 5, right? PPH3 means 3 phosphine group phenyl group, sorry, not phosphine, phenyl group, C6H5, 1 2 3 and oxygen 2 4 5. So this is the structure, right, and the mechanism. Similarly, we have one more named reaction which is similar to these two, right? That is nothing but Staudinger reaction. In Staudinger reaction, what we will do, same thing. Let me see, yeah. Staudinger reaction, R, this is also alcohol above the plane, right? And also above the plane, right? And here they make use of phosphine only, PH3 plus their dead we used, right? Diethyl azido dicarboxylate. Here also they used dead plus one more reagent, they use HN3, and the second one is PPH3 comma water. So this is also same, this is nothing but the Mitsonubu reaction, but one scientist made use of this azide compound, so this is named by Staudinger reaction, but it is same as Mitsonubu. So here what we get, dead means structure, N double bond N, here one electron withdrawing group, here one electron withdrawing group. You should remember, every time I need not write the structure, right? Electron withdrawing group, and phosphor will link here like this I have told. So it gets negative charge and phosphor gets positive charge, right? This is the structure, and this negative charge is satisfy HN3 structure, HN double bond N double bond N. This is minus plus, right? HN3. So what it will do, this negative charge take this proton and nitrogen gets negative charge, right? So what happens, instead of writing all this, let me write here only, nitrogen gets proton and this gets negative charge, right? This is nothing but azide group, azide, right? It has got 4 bonds, so it is positive, and this 2 so this gets negative. These things you should know. So what happens, here in substrate we have alcohol R, and which is above the plane, OH. So what happens, it will attack this phosphor and this hydrogen will leave as H plus. So this thing we know, PPH3, and alcohol is there which is above the plane, and here one R and here one R group, right? And here N, single bond N, here H, and here electron withdrawing group, and here also electron withdrawing group. So here N3 azide group is there. So what it will do, as phosphor oxygen bond is very stronger, oxygen has more affinity to phosphor, so this bond will be broken like this, right? Because phosphor oxygen bond is stronger than carbon oxygen bond. So this azide, which is nucleophile, will attack this carbon, electrophilic carbon, right? So what we will get, R SN2 reaction, because this is nothing but SN2, from backside it will attack, so inverted product we will get. So N double bond N double bond N, this is plus, this is minus. It can be written like this also, or they will write simply like this, below the plane N3 minus, right? N3 minus. So this is the structure. N3 minus, no need to write N3 minus because it is plus minus neutral. So N3 we can write it like that also, right? R N3. So inverted product, and the other product will be as usual same. What other products are? This bond will be broken like this, as phosphor oxygen bond is stronger and phosphor valence is 5, here 3, 4, 5 and 6 it will happen. So what it will do, it will give its electron density to nitrogen. So other products are PO, PH3, sorry, yes, PH3 means PH, phenyl group, right? C6H5 group is nothing but phenyl, and here one more is, here electron withdrawing group, here hydrogen, and here also hydrogen. These are the product. This is also nothing but Mitsonubu reaction, but using this scientist had made the reaction, so it is called Staudinger reaction, right? So this is about Mitsonubu reaction. So I have got 10 more minutes. Let us see one more Mitsonubu reaction. In next class, we shall discuss only Mitsonubu reactions only, but we shall start from this class only, right? So, few examples we will see. The first example is they have made use of this compound. Though the first example, same alcohol they have taken OH. This is R dash OH. To this they have added COOH group and PPH2. Why now it is PPH2? Because phosphorus valence is 3 and 1 lone pair, right? So 3 valency, 1, 2 and here 3 and 1 lone pair, right? And acid. So here acid group is also there and phosphorus group is also there. So it is act as dual character now. What we required, which we added separately in the reaction, but we got the same compounds in a single reagent, right? So dual character it will act, and they just add diethyl azido dicarboxylate dead, or also DIAP diisopropyl azido dicarboxylate we can use, right? And the base they used is NaOH. As they used NaOH, we got the product like this: R dash below the plane OH. Instead of NaOH, if they used HN3, then we used to get R dash below the plane N3 structure. Instead of this, if only no base, nothing is used, only this substrate is used, then here this will also attack, right? Or other acid if we add, we will get many products, right? Like nitrogen, we use NH2 minus, we will get R dash NH2, these nucleophiles. So here above the plane, here below the plane. If it is below the plane, there above the plane. So stereochemistry you should know. This is nothing but pure SN2, inversion of configuration. Above plane becomes below or below plane becomes above, right? So let us see the mechanism of it. The same mechanism. See here, what happens? This group is there, COOH and PH2 now. So diethyl azido carboxylate. If here also any other electron withdrawing group, not only carboxylate, C triple bond N, such electron withdrawing group is also there, then also the reaction will undergo, right? So instead of not specifying the anything, let me write only electron withdrawing group, and here also electron withdrawing group, right? So phosphorus is there, attacks, here nitrogen gets negative charge and this bond will be formed. Let me write here only directly. This bond is formed and phosphorus gets positive charge and nitrogen gets negative charge and it becomes single bond, right? So next acid is a H plus, it has got H plus donor, right? This negative charge take this H plus and becomes like this H, and this will become CO minus, right? So this is the substrate we got, and we are adding NaOH now, right? So OH minus is there. OH minus is their substrate, and this substrate is also there, alcohol R dash above the plane OH is there. So this OH will attack this phosphor, right? Because phosphor oxygen bond will be very stronger and oxygen has more affinity with phosphor, right? So what happens? PH2 and here benzene ring will be there as usual, and here COO minus and oxygen has attached, and this is above the plane, and here R dash, and other things are nothing but same. N electron withdrawing group, and here one hydrogen, right? So what happens here, as we are taking this OH minus, this will add to this carbon, which is more electrophilic. Why it is electrophilic? Because phosphor oxygen bond will be very strong and this bond will be broken like this, right? So the product what we will get, these things you keep on writing with me, so that if I rub it should not get problems, right? P double bond O, PH, and here benzene ring with COO minus. So see, valency of phosphorus is 5, right? 1, 2, 3, 4, 5. It is maintained. And here also nitrogen from water it will get NH, and here also H, and here an electron withdrawing group, and here one electron withdrawing group. As it attacks from below the plane, why it attacks from below the plane? It will be purely inversion SN2 reaction kind. So we get this kind of R dash below the plane OH will get. Instead of OH, if we add HN3, we used to get N3 minus, like I have told you in these reactions. So in next class, let us see few more reactions of Mitsonubu and we will stop it.